Welcome to The Explainer. We're all about taking big, complex topics and making them super clear.
You know, it feels like magic, doesn't it? But it's not. It all comes down to one of the most fundamental ideas in our modern world, the electrical circuit. Okay, so what is a circuit? Well, at its most basic, it's just a closed loop. Think of it like a racetrack for electricity. It has to travel from the start line, the power source, go through a device that does something, and then make it all the way back to the start. And if that loop is broken anywhere, game over. The flow just stops. All right, so here's our game plan for today. We're going to start with the basics of that closed loop, then talk about the two main ways electricity flows, AC and DC. After that, we'll meet the key building blocks, see how they connect in series versus parallel, combine them into more complex circuits, and then wrap it all up with why this stuff really matters.
Okay, let's dive right in. First up, that closed loop. We're going to get right down to the fundamentals of what makes a circuit, well, a circuit.
So this really boils it all down, doesn't it? Every simple circuit needs these three things. You've got your power source, say a battery, that's providing all the juice. Then you've got a component, or what engineers call a load, in this case a light bulb. That's the thing that's actually doing the work. And finally, you have the conductors, the wires, that connect everything into one big, complete, unbroken path.
But here's a twist. Not all electricity flows in the same direction. And that brings us to our next big idea, the two major types of current, AC and DC.
So the big difference here, the thing that separates these two, is all about the direction the electrons are moving. First, you've got direct current, or DC. I want you to think of this like a one-way street. The electrons are just cruising along nice and steady in one single direction. That's the kind of power you get from batteries. But then you have alternating current, or AC. This is totally different. The electrons are constantly changing their minds, reversing course, flowing back and forth, and that is the kind of electricity that's coming out of the outlets in your house right now. So, why the two types? Why does this even matter? Well, it turns out to be a really big deal. The reason our entire power grid runs on alternating current is because it solves a huge problem that DC has. You lose a ton of power trying to send it over long distances. AC power, which was championed by the brilliant Nikola Tesla, can be transmitted super efficiently for miles and miles, and that was the game changer that gave it a massive advantage over Thomas Edison's early DC systems. All right, so we've got our path, and we know which way the current is flowing. But what are the actual things we put in that path? It's time to meet the main players, the three fundamental building blocks of almost any circuit. First up, we have the resistor, and its name tells you everything you need to know. Its entire job is to resist the flow of current. The speed bump analogy is perfect. Resistors are all about control. They let engineers dial in exactly how much electricity gets to other parts of a circuit, especially the really sensitive bits. Okay, next up is the capacitor. This little guy stores up energy in an electric field. You can think of it like a tiny, tiny battery, but one that can charge up and then release all its energy in a split second. And that ability to deliver a super quick burst of power is absolutely vital. It's what makes the flash on your phone's camera work, and it's also used to smooth out the power delivery inside your computer. And that brings us to our third main component, the inductor. Now, if a capacitor stores energy in an electric field, the inductor stores it in a magnetic field. A perfect example is that chunky power brick for your laptop. Inside that thing, inductors are hard at work, smoothing out the flow of energy and filtering out any electrical noise. They're basically making sure your laptop gets a nice, clean, stable supply of power. Okay, so you've got your parts. Resistors, capacitors, inductors. Now, how do you hook them up? Well, that brings us to the two fundamental blueprints for connecting pretty much anything in a circuit, series and parallel. And this right here is probably the most important thing to get your head around. On the left, you see a series circuit. It's like a single-lane country road. The electricity has only one path it can take, and it has to go through every single component one after the other. But on the right, you've got a parallel circuit. This is more like a multi-lane highway. The current gets to split up, and different parts of it can flow through each lane at the same time. So it's really all about one path versus many paths. And that one path versus many paths difference has some really big consequences, which this table breaks down perfectly. See, in a series circuit, the current is the same everywhere, but the voltage has to be shared between all the components. In parallel, it's the exact opposite. The voltage is the same for every lane, but the current is what splits up. But check out that last row, because this is the big one. If one component breaks in a series circuit, the whole thing is dead. But in a parallel circuit, if one path fails, the others can keep right on working. And if you want a perfect real-world example of that weakness, just think about old-school holiday lights. We've all been there, right? One single bulb burns out, and the entire string of lights goes dark. Then you have to go through one by one, trying to find the culprit. Yeah, that's a series circuit for you. And that's exactly why your house is wired up in parallel. Think about it. Every single outlet, every light switch, is on its own little branch of the circuit. It's way more robust and practical. You can plug in a toaster, and it won't suddenly turn off your TV. Thank goodness for parallel circuits, right? But here's the thing. In the real world, very few circuits are just series or just parallel. The real magic happens when engineers start mixing and matching, combining all these pieces to create really specific functions. And that's what we're getting into next, building complex circuits. So when you start combining those components we talked about, you get these fundamental recipes. For example, you put a resistor and a capacitor together, you get an RC circuit. Those are great for making timers, like the delay on your car's windshield wipers. Or pair a resistor and an inductor to get an RL circuit, which is awesome for filtering audio signals in a speaker. And if you put all three together, the RLC circuit, you can create incredibly precise filters. See? Each combination gives you a totally new tool to work with.
But there's one combination that's really special, the LC circuit. It's also called a resonance circuit. And the way energy can kind of bounce back and forth between the inductor and capacitor gives it this one unique property, which leads to an application I guarantee you use all the time.
Okay, now I know this diagram might look a little intimidating, but the idea behind it is actually pretty simple. An LC circuit is designed to like or resonate at one very specific frequency. So what does that have to do with you? Well, every single time you tune a radio to your favorite station, what you're actually doing is adjusting the properties of an LC circuit inside. You're changing its resonant frequency so it can lock onto that one station signal and completely ignore all the thousands of others floating through the air.
All right, let's pull all these threads together and talk about the big takeaway. Why does any of this matter?
Because from something as simple as a light switch to something as complex as a radio tuner, it all comes back to these fundamental building blocks. Understanding how you arrange these components in a circuit is the key to understanding, well, our entire powered world. A closed loop, AC versus DC, resistors, capacitors, inductors, series, parallel. It's like learning the grammar of electricity. Once you know the rules, you can build anything.
So now that you know the basic blueprints of how electricity works, what's one device you use every day that you'll look at a little differently now? Thanks for joining us for this explainer. We really hope it sparked your curiosity.
Let's study more and like, share, and subscribe for such more content. And comment something you want to learn.